Okay, so in these sections, we are talking about improper integrals. Okay, so now before, for the integral that we are working with is we have the, again, we have from A to B, right? So we are talking about this. Okay, so this is what we are talking about, the definite integral. However, what if I have a function that is kind of like how about 1 over x? Then we have this. Okay, so if I want to find the area under the curve that is from 0 to infinity. Okay, now first of all, we know that in this case we have a vertical asymptote. Basically, we will not be able to get. That means we could get closer and closer, but again, never get to. That means this one, because when x is equal to 0 is undefined, right? Or when x approaching to infinity, of course, I know that the output is getting closer and closer to 0, but in some sense, it's never ever touched the y equal to 0 this line. Okay, so this is the idea about the improper integral. How do we actually take care of this type of integral then? Okay, so here is the idea about the improper integrals now. So in this case, if we have the integrate from a to t of f of x dx, except for every number for x is greater than or equal to a, then if I want to evaluate from a to infinity of f of x dx, what we could do is we could actually take a limit as t approaching to infinity, okay, of the integration a to t of f of x dx then, okay, provided the limit exceeds, okay. Okay, so same idea. If I want to get it from negative infinity to b, then in this case, what we could do is we could take the limit, assign t to negative infinity, and then take the integration from t to infinity. I'm sorry, from t to b of f of x dx. Okay. Okay. So then now the improper integral, okay, a to infinity of f of x dx, or n from negative infinity to b of f of x dx are called convergence if the corresponding limit exceeds, and divergence if the limit does not exceed. Okay, so in this case, convergence meaning what we the answer is a number. Okay, divergence meaning what the integral is either infinity or negative infinity. Then, if both from a to infinity of f of x dx and from negative infinity to a of f of x dx are convergence, then we define that the integration, that means the limit is from negative infinity to infinity of f of x dx is equal to, just like this one right here, right? Negative infinity to a f of x dx plus a to infinity of f of x dx. This is the idea right here, okay? So to this one, to this function right here, if I have y equal to 1 over 1 plus x squared, then the answer that I have, okay, again, we find the total area under the curve from negative infinity to infinity is pi. So in this case, this means it's convergence, because again, this limit exceeds, and also the answer is equal to pi, equal to a number then, okay? Okay, then now, let's try this problem now, okay? Now, to this one right here, I know that 1 over x squared basically is like this, right? Okay. And now, what I would like to do is, I would like to find from 1 to infinity. Okay. So if this is the case, then what do we need to do here is, we could actually take the limit as t approaching to infinity of 1 to t 1 over x squared dx. Okay. Now, remember to this one, we could actually change this t to r, then this will be r. If we change it to, that means, again, we could change it to any variable we want. Okay. But again, maybe we just keep it with t then. Then now, what do we need to do is actually, in this case right here, we could, then maybe let us work with this one, 1 over t, and then this is x to the negative 2 dx. Okay. So of course, in this case, I know that the antiderivative is actually exit. And now, what do we have? We are going to have the limit t approaching to infinity of negative x to the negative 1 divided away from 1 to t then. Okay. Okay. So then now, what do we need to do is we just need to keep going. Now again, remember from this step to this step, we take care of the integration already. And then now what we need to do is we will have this one is maybe let us take care of this one a little bit. Okay. And now it is equal to, we take the limit t approaching to infinity of 1 over t minus 1 over 1. Okay. Let's try this. And then, of course, we know that when t go to infinity, this go to 0. So therefore, my answer will be 1. Okay. So in this case, because this is a number, so then I will say that this is a convolution now. Okay. Okay, so then this is actually is the answer. Okay. And then let's try the next one. Is number 2 right here. Okay. Okay, so to this one right here, then let's see. If we have this, okay, now if we have this, then we know that the graph that we have basically is actually, it will be something like this then. Okay, so this is e to the negative 2x right here. And then now, of course, to this one, we are looking for from 2 to infinity. Okay, so then we could take the limit for t go to infinity, 2 to t, e to the negative 2x dx. Okay. Then, in this case, we could actually try to do this is the limit t go to infinity of 1 over negative 2, e to the negative 2x. Okay, and then you are away from 2 to t. Okay, then now we are going to have negative 1/2. We take the limit t go to infinity of e to the negative 2t minus e to the negative 4. Okay. And now we know that as t go to infinity, this whole thing right here is go to 0, right? Just from the graph, or we could actually have 1 over e to the 2t. Okay. And then this going, the denominator is getting bigger and bigger, so therefore the answer is equal to 0 then. Okay, so then now I will have negative 1/2 times negative e, let me write it like this. Okay, so then my answer will be 1 over root times e to the 4th. Okay. Yeah, easy, huh? Okay. Now the next one is actually is, I would like to talk about this. Now remember P is actually is a real number. Okay, it is kind of like any numbers here. Okay, so then in this case, let us try this problem now. Okay, so now to this one, basically what we need to do is we take the limit as t equal to infinity of 1 to t, 1 over t to x to the power p dx. Okay. Then I could have 1 to t of x to the negative p dx. Okay, so we could have this. Okay, then now what we could do is actually we could try to take the limit t go to infinity. Okay, so I will have this one is x to the negative p plus 1 over negative p plus 1. Okay, so now then what we could do here is I could take this out, so I have 1 over 1 minus p. Okay. The reason that I write like this because I will be able to, it's easier for me to analyze it, okay? Okay, so I have something like this. And then now, what I'm going to do is actually, I would like to replace this. So I have 1 over 1 minus p, and then take the limit t approaching to infinity of 1 minus t p minus 1 minus 1 over 1 to the p minus 1. Okay. And then let us simplify this. So I have 1 over 1 minus p, the limit t go to infinity of 1 over t p minus 1 minus 1. Okay. So now because p is actually all real numbers, right? So then in this case, we will be able to have 3 cases here. Okay. So let us try to analyze the 3 cases. For case number 1, it's actually if p minus 1 is greater than 0. Okay. In other words, p is greater than 1 then. So then now, let's see. I will have 1 over 1 minus p. One minus p. Take the limit. I'll go to infinity of 1 over t raised to the power of p minus 1. Okay, minus 1. So if p minus 1 is greater than 0, meaning what the denominator is getting bigger and bigger as t go to infinity. Okay, so therefore in this case, this is actually go to 0 then I will have negative 1 over 1 minus p, okay, or 1 over p minus 1 then. So if I have the integration from 1 to infinity of 1 x to the p dx, is equal to 1 over p minus 1. So in this case right here, if p is greater than 1, okay, then the answer is convergence. Okay, and now case number 2. How about if I have p minus 1 is less than 0? In other words, is p is less than 1. Okay. Then, in this case, we will have 1 over 1 minus p, the limit t go to infinity of 1 minus t p minus 1 minus 1. Okay. So you will see that if p minus 1 is less than 0, meaning what this number is negative. If it's negative, meaning what? It will be t to some power, right? So when t go to infinity, what happened to this whole thing? This whole thing goes to infinity. That means the limit does not exceed. Okay, so therefore this is divergence. Okay, and of course to case number 3, how about if p minus 1 equal to 0? So in other words, p is equal to 1. Then to p equal to 1, then I will have 1 to infinity of 1 over x dx now. Okay, so then let's try, what do we have? Maybe we could do this here. Okay, so if I take the limit 1 go to infinity of 1 over x dx, then it is equal to the limit t go to infinity of 1 to t 1 over x dx. Then in this case right here, I have the limit t go to infinity of natural log of x. Okay. Then of course, actually I don't need absolute value, right? Because t is greater than 1 then, right? Then my answer will be the limit t go to infinity of natural log of t minus natural log of 1. Okay. Now of course, we know that natural log of 1 is equal to 0, but natural log of t, when t go to infinity, is go to infinity. Again, this is divergent. Okay, so meaning what? This is equal to infinity, so it is divergent. Okay. Okay, so basically, when we have the integrate from 1 to infinity of 1 over x to the power p dx, we have 3 cases. The first case is if p is greater than 1, then my answer will be 1 over p minus 1, and it is a convergence. Okay, so let's see if this is the case. Do you remember that our first example? In this case, p is greater than 2, and then the answer here, okay, which is equal to, again, in this case, p is equal to 2. Remember the answer is what? Is 1 over p minus 1, right? So which is equal to 1 over 2 minus 1, which is 1. This is exactly what we have here. And then if p minus 1 is less than 0, which is p is less than 1, if p is less than 1, then actually this is divergence then. And then if p is equal to 1, just like the last case, right? If p is equal to 1, then it is also a divergence as well. Okay? So this is what we call the p integral then. So therefore, again, this is what we have for the p integral. So for the p integral are particularly important because they are often used to determine the convergency or divergency of more complicated improper integrals by means of the comparison test. Okay. So then let's try the following example then. So in this case right here, sin p is equal to 20 over 19, which is greater than 1. So meaning what? This integral essentially is by the p integral, right? It is convergence. So by the p integral, then it is equal to 1 over p minus 1. Then it is 1 over 19. So the answer is equal to 19. And then it is convergent then. Okay. And then to this one right here, so we could say that sin p is equal to 1, that means by the p integral, the answer is equal to infinity, so which is divergent then. Okay. Okay, now you will see that to the p integral, this is just started from a, okay, where a is positive number. So of course, to me, I just use that a is equal to 1, right? But a could be any numbers that is greater than 0 then. This is how we use the p integral, okay? Okay, so now let's talk about how do we actually work with the unbounded integrand then, okay? So in this case, or maybe we have it in infinite discontinuity at the endpoint, okay? So again, the cases is if we have it from A to B, where B is actually is undefined right here, right? Even though B is defined, but again, the function is actually is we may have a vertical asymptotes here at x equal to b, or we may have a vertical asymptotes at x equal to a, okay? Or in this case, if we evaluate from A to B, but the vertical asymptote is in between, that means at C, where C is in between A and B. Then in this case, how do we actually take the integral then? So basically, what we need to do here is we are going to set up for the first case is actually in this case right here, because B is a vertical asymptote. Okay, so therefore we could take the limit t approaching to B from the left in the integral from a to t of f of x dx. Okay, and then to case number 2 is the vertical asymptote is x is equal to a, right? So then we could take the limit t approaching to a from the left hand side, okay, from the right hand side, integrate from t to b of f of x dx. Okay, and then of course to case number 3, then in this case what we need to do is we need to separate into 2 integrals. Okay, and then from there, then we take the limits, just like the case A and B, to take care of case number 3 then. Okay. So therefore, it is really important for you to know the graph first, okay? This is really kind of important too. Okay, so then now, let us try to see how do we actually take care of this integral then. Then, to this one, I actually have dx over x plus 2 raised to the power of 1/3. Okay, so then now to this one right here, we know that the graph in this case right here is we are going to have a vertical asymptote at x equal to -2. Okay, and then to this one, we are going to have something like this. Okay. Okay, so then now what we want to do is we would like to evaluate from 2 to 4. Okay. Then we know that x equal to -2 is a vertical asymptote here. Okay. Okay, so then now we could actually do this is we are going to take the limit t go to -2 from the right hand side, okay, from t to 4 dx over x plus 2 to the 1/3 power then. Okay, so then now we are going to work with the integrand now. Okay, so in this case then we could have this is we take the limit t approaching to -2 from the right hand side, t to 4 x plus 2 to the -1/3 dx. Okay, of course you could let u equal to x plus 2 and then work it out, but since we already have a lot of experience, then we could just take the evaluate this then. Okay, and now okay, so then to this one right here, I will have 3/2 x plus 2 to the 2/3. Okay, evaluate between t to 4. Okay, then now we could continue to finish this then. Okay. Now we could use direct substitutions to actually do this then. Then of course in this case we actually see the limit exceed. Okay, so then it is actually is converged. Okay, so then the next one. We know that when x equal to 0, is actually the whole thing is undefined. Okay, and then we have it from 0 to 1. So in this case, we could take the limit t approaching to 0 from the right hand side. Okay, and then we have t to 1 of e to the square root of x dx over square root of x. Then to this one right here, we know that this one right here is actually if I let u equal to square root of x, then the derivative will be -1 over square root of x, right? So then in this case, not negative but positive then. Okay, this 1 over square root of x dx. So now we could actually have this one is the limit t equal to 0 plus integrate e to the square root of x t to 1. Okay, now if you don't know what I did here, then maybe I need to be careful a little bit. So let us work on this side right here. So if I have e to the square root of x dx, okay, then I'm going to let u equal to square root of x. Okay, then I have du will be 1/2 okay. Then du will be 1/2 x to the negative 1/2 dx. Okay, so which is du is square root of x. Okay, 1 over square root of x dx. So then in this case, I will have e to the u du. Okay. Okay, so anyway, then now I have this. Okay. And then after we have this, then I will have to take the limit t go to 0, okay, of e to the square root of x minus e to the square root of t. Okay. So therefore, in this case right here, I will have 2 times e minus e to the power of 0. Then my answer will be 2 times e minus 1. Okay, so then this is actually is again how we take care of this type of problem then. Okay, so now the last one that I would like to talk about is the comparison test for the improper integrals. Okay, now assume that f of x is greater than or equal to g of x greater than or equal to 0. Okay, so meaning what? The function f and g is actually is about the x-axis. Okay, and for x is greater than a. So if the integral from a to infinity of f of x dx converges, then the integral from a to infinity of g of x also converges. Okay. Now the idea to this one right here. Okay. So again, we have two functions. One function is the f of x. This is the f functions, and then we have a g functions like this. Okay. And then for x is greater than a. Okay. So in this case right here, if we have the biggest, for example, the first case, right? We know that this case right here, f is actually is, again, integrate from a to infinity of f of x dx is convergent, then the function that is smaller, which is g, then must be convergent then. On the other hand, to the second situations, if the integration from a to infinity of g of x dx is divergent. If this is already divergent, then the biggest, that means the number, the bigger function f must be divergent as well. Okay, so this is actually is the idea about the comparison test. Okay, with the what the comparison says that for non-negative functions, then if the integral of bigger function converge, then the integral of the smallest function also converge. If the integral of the smallest function diverge, then the integral of the larger function also diverge. Then. Okay, so this is actually the idea. Okay, so now to this one, I would like to work with the comparison test. Okay, to determine whether or not the integral is actually is convergence or divergence. Then, okay. Okay, so then now let's just check with the functions. Now, first of all, if I want to say that for x is greater than 1, okay, then we know that x to the power 3 plus 2x plus 4 must be greater than or equal to x to the power 3. Okay, we know this. So therefore, if we take the square root, then of course, okay, then we know this. Then now, if we take 1 over then which one is actually bigger? Okay, now let me use a simple number for you to be understand that. Now you know that in this case 3 is greater than or equal to 2, right? If we take the reciprocal, okay, then we know that this is about 0.3333 and then this is 0.5. Okay. So therefore, in this case, if we know that this number is bigger than this one, then the reciprocal must be the other way around. Okay. So then now we know that this function right here, okay. Then in this case right here, the integral one go to infinity of dx over x to the 3/2 convert by the p integral. Okay. That means in this case, by the comparison test, that means this integral right here must be convergent then. Okay. By the comparison test. One go to infinity of dx over e to the power 3 plus 2x plus 4 raised to 1/2 also converts. Okay. So this is actually the idea about the comparison test then. Okay. Okay, so when now it is your turn, go ahead and try this problem now. Okay. Number 9. Okay, so how do we actually analyze this? Okay, we could actually say that for all x, we know that the absolute value of psi of x is actually less than or equal to 1. We know this. Okay, of course, because it is absolute value, so then this one is always positive, right? So. Therefore, for all x is not equal to 0, that means psi of x over square root of x must be less than or equal to 1 over square root of x then. Okay. Okay, so then now we do this. Okay. Then the integral zero to 1 of 1 over square root of x dx is equal to 1 over x to the 1/2 dx. Okay. And then remember by the p integral. So to 1 of 1 over x to the 1/2 dx backward. Convert. Okay. Because again, p is greater than 1, right? Then in this case, then we could make the conclusion now. Since 1 over square root of x is greater than or equal to psi of x over square root of x by the comparison test. Zero to 1 of psi of x square root of x dx also converge. Okay. So this is actually is how we use the comparison test. Okay. So make sure that remember this. If the integral of the biggest function converge, then the integral of the small function also converge. On the other hand, if the integral of the smallest function diverge, then the integral of the larger function also diverge. Okay. And of course, to this section right here, I just introduced how do we actually work with the improper integral, meaning when the integral is go to infinity, or when we integrate from the vertical asymptotes, right, to some numbers here. Okay, so we could use improper integral to work it out the problem then. Okay, so that's it. Thank you. Okay, so now let us work on the last problem. Okay, how do we use a comparison test? Okay, to test if this integral is convergent or divergent now. Okay, so to this one right here, first of all, we know that for all x, okay, then the absolute value of psi of x basically is bounded between 0 and 1. Okay, we know this. And then now, to this integral, we know that we could not have it equal to 0, so then we could say that for x is not equal to 0, then the absolute value of psi of x over square root of x must be less than or equal to 1 over square root of x then. Okay. All right. So now we know that this is the biggest functions. So then now what we could do here, then we could actually evaluate this then. 1 over square root of x between 0 and 1 and dx. Okay. Now we know that when x is equal to 0, the whole thing is undefined. So what we need to do is actually we will take the limit as t go to 0 from the right hand side of integrate between t and 1 of x to the negative 1/2 then. Okay, now notice I didn't use the p integral. The reason is, in this case, remember the p is 1/2. We only know that when p is greater than 1 or less than 1, right? So we don't know that if p is between 0 and 1, then what do we know? Okay, so we could not use the p integral to finish this problem. So therefore, again, we have to do a hard way that we need to work with the integral then. Okay. And now, then we have the, okay, so it will be the limit t go to 0 from the right hand side of x to the negative 1/2 plus 1 over 1/2 here. Okay. Then, of course, I will have 2 times x to the 1/2. Okay. Integrate between t to 1. And now we have the limit t go to 0 from the right hand side 2 times. Okay, so I will have 1 minus t to the 1/2 now. Okay. So of course, in this case, we know that this is actually is equal to 2, because again, this is 0 right here, right? That means this is converged. Okay. Okay. Then now, if the biggest function is converged, then the smallest function is also converged then. Okay. Since 1 over square root of x is greater than or equal to absolute value of psi of x over square root of x. By the comparison test, zero to 1 of absolute value of psi of x square root of x dx also converge. Okay. That's it. So, okay. So then now again, you will see that to this section right here, we learn how do we actually take care of the improper integral. Is when maybe you have like from a to infinity, or from infinity negative infinity to b, right? Or if we have a vertical asymptotes, then if I evaluate from a to the vertical asymptotes, or from the vertical asymptote to b, something like this, then again we could use the improper integral to work it out. Okay, which is work with the limits. Okay. And then also the last thing that I introduced is I introduced the comparison test. Okay, so remember, if the integral for the biggest functions converge, then the integral of the smallest function also converge. If the integral of the smallest function diverge, then the integral of the larger functions also diverge. Okay. Okay. So yeah, that's it for today for these lectures. Okay. So thank you.